This is Math 125. Today we're going to talk about Section 3.3, Measures of Variation in our online class. Alright, as we know, when we are given data, raw data, large groups of numbers, there are two questions you should always ask first. What is the center? As we saw, there's four different ways to measure center from Section 3.2, mean, median, mode, and mid-range, and how far is it spread. Alright, consider the following data. Now, what we are going to give you here are waiting times at two different banks. We're going to call the banks Jefferson Valley is one of the banks, and Providence is the other bank. In Jefferson Valley, there is one waiting line. You know how that works. Everybody is funneled into the same line, and as tellers become open at the bank, they drift off, they branch off to different tellers. So everyone waits in the same line pretty much, and in Providence we're going to have individual lines. Each teller has an individual line leading up to each customer. Alright, I'm going to write down the waiting lines. I'm going to write down 10 waiting times for each of these banks, and they are going to be in minutes. Waiting times in minutes. Give me a minute to write this down. I want to make it nice and neat. 6.6, 6.5, 6.6. And notice this data is ranked from low to high. Alright, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 waiting times for 10 different customers, all waiting in the single line at Jefferson Valley Bank. How about Providence? And 10.0. Alright, as you might expect, in the single line bank, Jefferson Valley, well, the data values are more tightly compressed than in Providence Bank. In Providence Bank, there's more spread of the data. If I ask you for the center for these two sets of bank waiting times, well, it turns out the means are all the same. Or the mean for both banks is the same. If you take the time, the median, if you take the time to grind out the mean and the medians are the same also. Of course, the mean is, in this case, the median is the mean of the middle two, and they both turn into 7.2. The mode, the most frequent measure of data in both sets, is the same at 7.7 for both sets of data, and even the mid-range is the same at 7.1 for both. Alright, so clearly measures of center don't really tell the whole story in a data set. We need another type of measure of spread, and that's what Section 3.3 is all about. We need a numerical measure of spread, or variation, our book would call it. Not just looking at a data set and saying, oh, one looks more spread out than the other. Alright, we've got three numerical measures of spread that we're going to talk about in this section. Let me write them down. That'll be a little more formal. Measures of variation, our book would call it. 3 different ones we're going to talk about here. Range, standard deviation, and variance. So just like we had 4 measures of center, we are going to use 3 measures of variation. And let me define these to you one at a time. Range. Well, as you might guess from the name, all it is your high minus your low value. And of course, this is a crude measure of spread. It depends slowly on your extreme values, so it is highly susceptible or vulnerable to outlier effects. So range is a crude measure, vulnerable to flukiness or outlier effects, and hence it's just not used very much, but is sometimes used, particularly with the repeated calculations in computer type programs. Alright, next up the line is standard deviation. And standard deviation is the gold standard for measuring variation in a data set. Standard deviation. Well, if the mean measures the center, then the standard deviation is your average distance from center. I've mentioned that in class before. Let me write that down. Your average distance from center. And that's kind of an informal definition. The formal definition of standard deviation goes like this. Well, first of all, let's give you a symbol for standard deviation. It's the lowercase letter S. And let me build up the formula here. If x is a variable that represents each data value, I'll write x here and say that's my variable representing each individual data value. If from each data value I subtract the mean of the set, then I will take those differences from mean and I will square them. Makes them all positive. Then I will add up all those squared differences from the mean. Then I divide by little n minus 1, your sample size, take away 1, and finally take the square root of this mess, and that is your standard deviation. Okay. In the textbook, they'll refer to standard deviations as lowercase s. In the Texas Instruments calculator, as I mentioned in class, they use the rather peculiar symbol cap SX. Cap SX, that's your standard deviation in the Texas Instruments jargon. Alright, notice, because your standard deviation is a square root, well, it's always positive. Okay? And again, gives your average distance from the mean. And we'll work out an example highlighting that. Please notice your SD is a number, and the higher the standard deviation value, that means you've got more spread in your data. Higher SD value, more spread. Alright, the good news is the calculator, just like it computes a sample mean, when you plug in values into list L1, you can also compute your standard deviation from the with the calculator. So let me write this down. Calculator will compute your SD. And remember, Texas Instruments calls it CAP-SX from raw data. That's the good news. The bad news is I'm going to ask you once on a pencil and paper exam and an in-class exam to compute SDs by hand using the above formula. Alright? So, write that down. Can also use the above formula for SD. Oh, and by the way, SD is my abbreviation for standard deviation. You'll hear me use that a lot, both in online and in face-to-face classes. We can also use the above formula to compute standard deviation by hand. Well, we do use the calculator a little bit in this, but we don't use the calculator in statistics mode. I'll show you how that works in a minute. Okay? Let me give you an example of a data set. Let me start out. Let's see how much. I'll put how to compute standard deviation by hand. To do this by hand, I use what I call the table method. Now beware, the book for some reason doesn't talk about this table method, so you won't find it in the textbook, but I am going to ask you to do it at least once in a pencil and paper exam that you take in class. Let me give you an example here. Find the standard deviation for the following data. Alright, I'm going to give you a nice, simple data set consisting of the following 5 integers: 3, 4, 7, 9, and 20. And if I was to guess, let's take a guess. Let's see. What would be the average distance from the mean here? I don't know. I would guess the mean would be about 7 or 8 or so. And your average distance from the mean, well, some values are farther away from the mean than others, but overall I might guess, I don't know, 5 or 6. Let me write this down as a guess. 5, possibly 6 is your average distance from the mean. Alright, that would be my guess for S. That's not a 5 there. That's a little s. Let me erase that. Let me see if I can make this look more like an S here. Little s equals 5 or 6. That's just a guess, just by looking at the raw data. Let me write down the formula for sample standard deviation. Again, we've lost it up in the stream. So I take each data value, I subtract the mean, I square those differences from the mean, I add up those squared differences, I divide by n minus 1, and then take the square root of this entire expression, and that is my standard deviation. Alright, I want you to notice something. Notice x bar is involved in this computation for standard deviation. So we must know the sample mean before we compute the standard deviation. Let me write that down. We must have x bar to compute S. Well, so we can easily compute x bar for this sample. I add up 20 plus 9 plus 7 plus 4 plus 3 and divide by n. That's 5. That turns into an 8.6. Alright, so the mean for the above sample is 8.6. Alright, so what I'm going to do now is invoke what I call this table method. What I will do is make a table with 3 columns. I'll let the first column be a list of all the given data values. I'll fill that in right now. 3, 4, 7, 9, and 20. Alright, then my next column, I'll take each data value and subtract the sample mean of 8.6. I might as well fill that in right now. So I get minus 5.6, 3 minus 8.6 is minus 5.6, 4 minus 8.6 is minus 4.6, 7 minus 8.6 is minus 1.6, 9 minus 1.6 is positive 0.4, and 20 minus 8.6 is 11.4. Okay? Alright, now, in my third column, I'll take all those differences from the mean and I will square them. Alright, so if I fill in these values here, 31.36, and keep as much decimal accuracy as I can stand here, your calculator gives you 10 digit accuracy. I don't know if I want to write down 10 digits for each of these pending calculations. Alright, so what I'm looking for is the sum of that third column. The sum of that third column is going to be the numerator of this fraction under the root sign. Alright, summation x minus x bar squared. So let me go back down here. Remember, sigma for summation. Alright, I add up all these values and I get 185.2. Alright, let me go back to this standard deviation formula now. Little s equals square root summation x minus x bar squared over n minus 1. Again, the numerator of this fraction is this value, 185.2, the sum of that third column. So let me substitute that in. So s then equals the square root of 185.2 divided by, well, n minus 1 is just going to be your sample size, take away 1. If n is 5, we had 5 elements in our data set, then 5 minus 1, n minus 1 will then be 4, right? 5 minus 1 is 4. So I stuff in a 4 in my denominator, and I think the worst is over. If I grind this out on my calculator, I get a value of 6.8044, and your calculator carries this out to 10 decimal places. Our data was all in whole numbers, so I'm going to say rounding this off to the nearest tenth is just fine. So I'm going to say our standard deviation for this set is about 6.8. Okay? And you'll recall, if I go up the screen here, we guessed about 5 or a 6 for my average dispersion from the mean of 8.6, so that's about right. That's kind of what I expected, somewhere in the ballpark of 5 or 6, okay? Alright, so that's how you compute a standard deviation by hand. What I call by hand is with this table method. Alright, so you now have a worked out example recorded and available for you to review and study for our first test, which is coming up. I mentioned calculator also computes SD. I can check this value with my calculator. Alright, well, the first thing I got to do, just like I found sample means with the calculator, You've got to clear out your old data, enter in your new data, and then execute the proper operator to find one variable statistics. Let's review that. To clear out the old data, you press Stat, Edit. Typically we do most of our work in list L1 here, so clear list L1 like we told you to in class, and enter in the above new data. And what was it? 3, 4, 7, 9, and 20 in list L1. Okay. Alright, once you've cleared out the old data, entered in the new data, we then press again Stat and Calc. Select and enter your one variable stats command. Press enter twice. And you'll see our one variable statistics summary for our data. And there's many things in this list. Well, the first thing you'll see at the very top of the list is 8.6. That refers to our sample mean. And remember, cap SX, you'll see hopefully the familiar value 6.8044 and change. This, in Texas Instruments jargon, is the sample standard deviation, which agrees with what we got doing it by hand. So 6.8 would be a fine and reasonable value for the measure of spread of this data. Alright, this is what I call my sample standard deviation. We'll talk about that in a minute. Because it's based on values from a sample. Again, 6.8. If your standard deviation, if your sample standard deviation is 6.8, that's a little s there. What is that telling you? Alright. Again, your sample standard deviation is a measure, a numerical measure of spread or variation of data. If your SD is 6.8 in your given data set, that means the average deviation from the mean is 6.8 units, high or low. And that more or less agrees with what we might estimate by inspection. Again, please note, you will be asked on the first paper and pencil in-class exam to compute SD, what I call by hand, using the above described table method, once. Okay? And again, in a paper and pencil exam. After that, we will forever use the Texas Instruments calculator or even Minitab to compute standard deviations. Alright, let me get a fresh screen here. Alright. Alright, so we've talked about range. We've already defined it. We've already talked about standard deviation. Defined it, showed you two different ways to compute it. Alright, let's talk about variance. We may recall variance was the third measure of variation in our section 1.3. And I can define variance very easily. This is the symbol we use for variance, s squared. Well, all we're telling you here is that the variance is the square of the standard deviation. Well, that means it's your familiar standard deviation formula. Oops. Should get it a little more horizontal. Oh my god, what happened? Hang on. Fill that in. Alright. It's your familiar standard deviation without the square root sign. Alright, so essentially if you know your standard deviation, you also know the variance just by squaring it. So, if, like in our prior example, your standard deviation was 6.8, then the variance is nothing more than the square of the standard deviation. It's going to be 6.8 squared, which of course is 46.24. Alright, variance is used in upstream formulas towards later chapters in the book. Let me write that down. Variance is used as a variable in formulas in later chapters. So it is used. So I want to be sure to cover it here in our introductory chapters. Variance, simply the square of the standard deviation. Let me get another screen here. Let's see. Alright, I'm going to pause. Alright, let's talk about the idea of sample versus population regarding standard deviation calculations. Well, you've seen me write this diagram up on the board many times here. We've always got populations to worry about, and they're too big to study, so what we do is draw samples. Alright, we already know the difference between a sample mean and a population mean. Now, they are measures of center of essentially two different bodies of data. Well, one is the subset of the other. Alright, the terminology or accepted symbology for sample mean is x bar, as we know, and the population mean, as you recall, is mu, a Greek lowercase letter mu. Now, you can take standard deviations of a sample or a population, I suppose, in theory anyway, but those may be different values, and we give them different labels. Now, most times when we say standard deviation, we are really talking about a sample standard deviation. Again, a standard deviation drawn from a sample, and that is, of course, little s. We've already defined how to compute that in the past half hour or so. What I want you to be aware of is there is an analogous measure of a spread of a population. We call that a population standard deviation. And we refer to that quantity as the Greek lowercase letter sigma. Alright, so sample SD is S, and population SD we refer to as sigma. So beware of that and be able to differentiate those two ideas. One more topic I want to talk about today is skewness. What does it mean to skew things? In the old style TVs they had a skew control, and you may be familiar with the concept of skewness from old style televisions. Well, what I'm going to start out with here is a symmetric distribution of data. By that I mean there are, let me try to see if I can get this a better line here. By that I mean there is a vertical line of symmetry about which the distribution of data has vertical symmetry. Alright, in this particular symmetric distribution, you've got not too many low values, not too many high values, but most of your data is piled up near the center. Okay? Alright, in a symmetric distribution, the mean will equal the median. And that's not always true, as we'll see. The mean is always what is sometimes referred to as a balance point of a histogram type distribution of your data. Alright, again, in a symmetric distribution, the mean will equal the median. That means the geometric center of this data will be equally split. We'll have half the data above the mean and half the data below the mean. Okay? Not always true, as we'll see in skewed type distributions. What I'm going to do is take this same data set, the same symmetric distribution data set, and I'm going to doctor it a little bit, at least in the abstract. I'm going to take the same data that was symmetrically distributed, and I'll ask you to consider this in your mind. Replace the lowest values of this data distribution with even lower values. Alright, if I was to draw the resulting distribution, I think you'll agree with me, it's like pulling that left tail off further to the left. Right? It's like skewing the distribution to the left. Let me write that down. I'll say the tail, the left tail, is pulled to the left. Okay? And we call this a skewed left distribution. Now, in this distribution, the median is the same. Just because you're taking out low values and putting in even lower values does not change the relative measure of center that the median describes. But what does happen is your mean is lowered. I may be exaggerating this in the diagram, but certainly you can appreciate by putting in more extreme lower values into your data set will alter the mean, but not change the median. Right? So in a skewed left distribution, typically what happens is the mean is less than the median. Okay? Now I want to do the same thing with a skewed right distribution. Again, take your original data set in your symmetric distribution, but I will replace the highest values with even higher values, making them more extreme. Well, I think you can appreciate what's going to happen. Basically, the left portion of the original distribution is going to be the same, but my tail is going to be pulled off to the right. So I will have a skewed right distribution. So let me write that down. Tail is pulled to the right, and we end up with a skewed right, or sometimes called positively skewed distribution. in a skewed right distribution, well, just by taking highest values and replacing them with even more extreme values, the relative position of the median will be the same. Remember, the median is unaffected by outliers. Right? But certainly your average value, your center value of mean, will be affected because the mean takes every value into account, I should say. So in a skewed right distribution, the median is the same, but the mean, it turns out, is usually greater. So in a skewed right distribution, the mean tends to be greater than the median. Alright, we've just hit the 36-minute point, so we'll call it a day. And this concludes section 3.3 online class for Math 125 Statistics. That is all.